Okay, so we're supposed to find the interval convergence of the following. And we're given the infinite sum from 1 to infinity of 2 to the n over n times x to the n. Alright, so here, like I said before, we're going to be making good use of the ratio test. So we have our rho equals limit as n goes to infinity of a sub n plus 1 over a sub n. So we're going to put in an n plus 1 wherever we see an n over n plus 1 here times x to the n plus 1. Okay, and this is over our given a sub n, which is 2 to the n over n times x to the n. Alright, so this will turn into, we're going to break it down. So we have 2 to the n times 2, right, over n plus 1. And then we have an x to the n times another x. And this can be, well, I'm going to write these because these x things, they're on the top as well. So I'll write that x to the n times x, that's an n, sorry. And then, so we can flip up the bottom fraction. And so we'll have an n over 2 to the n times x to the n, alright? So the x to the n's cancel, the 2 to the n's cancel, and we're left with this, which, I mean, we can put the, yeah, so let's rewrite that. So we have rho equals limit as n goes to infinity of, wait, hold on. Okay, so we have a 2x times n over n plus 1, right? And then this, we can bring the 2x, the absolute value of 2x, outside, because in this limit, as n goes to infinity, that's a constant, right? So our variable x here, that's not concerned with the limit part. So we'll bring this out in front, and then we have limit as n goes to infinity, absolute value n over n plus 1. And this is actually going to tend to 1 in the long run, right? Because we have the same rate of growth here. So that's going to tend to 1, so this thing is 1. So our rho ultimately equals absolute value of 2x. And then we have to make this less than 1, right? In order for the sequence to converge, or the series to converge. So then we get that x, absolute value of x, is less than 1/2, which means centered around 0. Then our interval of convergence, as of now, is from negative 1/2 to positive 1/2, okay? So now, remember at this point, so this is our temporary, I guess you can consider it, so temporary interval of convergence, and it's only temporary because now we have to check the endpoints, right? So keep this in mind, and we'll check the endpoints now. So let's do negative 1/2 first. So we have from n equals 0, or actually this is 1, sorry, n equals 1 to infinity, and then we have our 2 to the n over n, and we're plugging in a negative 1/2 for the x spot, so then we have negative 1 to the n. So this is going to be the following. We have 1, and then this is actually, these two can combine, basically, the 2 and the negative 1/2 into a negative 1 to the n over n, and as we know by the alternating series test, we know that this converges, right? Because it's a harmonic series, but it does have this factor of negative 1 that helps it converge. So this converges. So basically we're going to have a square bracket on the left side of negative 1/2, okay? And then we have to determine what happens after the positive 1/2, right? So now we'll evaluate it at x equaling 1/2. So let's do the same thing. We have 1/2 here to the n. So this is going to equal basically the same thing, except for now we have a positive 1 to the n, which is just 1 over n. And this, as we know, this is a harmonic series which diverges. So we're gonna keep this round bracket here. So our interval is gonna look like -1/2 to 1/2, including the -1/2. Another way to write this is -1/2 less than or equal to, we have this equal part, and then less than 1/2. So the square bracket corresponds to a and equal to, or equal to, I guess, this line under here. Yeah, so that's it for that problem. This is our interval of convergence.